the central limit theorem. As the sample size approaches infinity, sample size approaches, for example, this is the sample size approaches to infinity, the distribution of sample means will follow normal distribution regardless of what the parent population distribution, usually 30 or larger. The mean of this distribution of sample means will also be equal mean of the parent population. The mean of this distribution of sample means the mean of the distribution of sample means will also be equal to mean of the parent population. For example, this one is equal to parent population. If x1, x2, the xn all have if x1, x2 and up to xn all have mean mu and the variance sigma square sampling distribution sampling distribution x bar equal to summation xi divided by n. If x1, x2, if x2, x1, xn all have mean mu and variance sigma square, then sampling distribution x bar, this one, x bar equal to summation all from x1, x2 up to xn, okay, xn divided by, this is how much, divided by this n, okay. E of x bar equal to mu variance of x bar comma sigma square n. E of x bar equal to mu, that is, then variance of x bar, we can say sigma variance for variance of what we find x bar, then sigma square we have to multiply, then divide, we have to put that n total value, okay. Here mu value you have to put this for E of x, for this one, for mu like this, for variance like this. Using central limit theorem for large n, x bar approximately equal to n of mu square divided by n. For large n, number of n's, that n is there, no, up to large is there, then x bar is approximately equal to total n, then mu. What do you find that mu? What do you find that sigma square? Then that n. Okay. If we are interested on p, if you are interested on p, a portion or the probability of event with two outcomes, two outcomes, we use the estimated p proportion times we see the event data, the sampling distribution of uh, p cap unbiased estimator of p. It means b cap if you are telling unbiased estimator of p, unbiased estimator of p has expected value p and standard deviation root 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 p p what after that we have to minus from 1, that p, then how much we are getting you have to multiply, divide we have to how much we are getting number, how much that number of times x1 x2 x3 mentioning already we say have seen, no? By the central limit theorem, large n sampling, how many numbers n, okay, large number n, the sampling distribution, if large number n, then sampling distribution how p cap approximately n for large how much coming, then p probability, this one also probability, and 1 minus we have to minus that probability, then we have to multiply, okay, then divide we have to how many sampling, number sampling, this much sampling we got this much probability, we physically meaning we have to minus that from 1 how much we are getting p, then you have to multiply with the probability, that much, that is the sampling distribution. Okay, is that static, yeah, is that score is the distance of a data point from the mean. Z score is the distance data point from the mean expressed in units standard deviation, this is the mean, okay. Okay, the Z score for a value from population is Z equal to x minus mu divided by sigma, that is a population, how much population we have to, how much x is there, then we have to minus the mu from that x, then how much we are getting sigma value, this much is sigma value, this much is there, this is the population. Conversion to Z score place distinct populations under same metric. Conversions to Z score place distinct population on a same metric. We are interested in the probability of a particular sample mean. We are interested in probability of particular sample This is a particular, for example. Particular sample mean we are interested in probability of particular. This much only we are interested, for example. Okay, particular sample. This is the particular sample. Okay, we can use normal distribution. Normal, this one we have to use even if you do not know the distribution of the population. Population how much you don't know, from which the sample was drawn by calculating Z-statistics. Then Z-statistics, that is population, equal to how much X bar. Then we are going to reduce from this mu from this one. Then we have to divide sigma divided by root 2n. Root 2n, how much we are getting, that one we have to put in the root. This much root n, this much sigma is there. So after reduction this value put, so this much for this. So we got after minusing mu from X bar, this is the population Z. So if we find this one, so you have to follow. The standard error of the mean. The standard error of the mean. What you have find here? The standard error of the mean is the standard deviation. For example, this is the mean. Standard error. This is the mean. So standard error of the mean, this one. What we have find, this one is the standard deviation. Is the standard deviation, okay, of the sampling distribution. Of the sampling distribution. Of the sampling. If describes the mean of multiple members of a population. Describes multiple, it describes the mean of multiple members of population. Multiple member of population. It describes the mean of multiple members of multiple members means this one, okay. Mean member of population, okay. It is always smaller. This is the for physical meaning, for understanding purpose, for that concept. This is sometimes not easy to understand also. So for physical meaning, for understanding purpose, we are just for explaining. It is always smaller than the standard deviation. It is always smaller than standard deviation. Smaller. So smaller than standard deviation. Sorry, like it only. Okay. The larger outer our sample size is the smaller is the standard error. The larger our sample size, the larger our sample. This is the sample, no? The larger sample size is smaller the standard error. So the standard error small only, not big. Less we would expect our sample mean to differ from the population mean. So this is This is the population mean.